You're staring at your console and something is wrong, but you can't say precisely what. The deployment failed. That part is clear, but the stack isn't in the state it was in before you started. It isn't in the state you were trying to reach either. Resources exist that weren't there this morning. Other resources that should have been created aren't there. Some of the new resources have already been picked up by other systems, monitoring agents, service discovery, auto-scaling groups, systems that now have references to things that may not work correctly. The rollback that was supposed to clean this up has itself partially failed. You have a delete operation stuck in progress on a resource that something else is still using. The status on your CloudFormation stack reads rollback failed. 3 words, technically accurate, completely unhelpful. A state that tells you the provisioning failed and the cleanup failed, and you are now in a place that has no runbook, no automated recovery path, and no obvious next step. How did you get here? What actually happened between apply started and rollback failed? And the question nobody wants to ask out loud is, the system actually broken, or does it just look broken? Working backwards from this state is the only way to understand it, and understanding it is the only way to clean it up safely. To understand how a system ends up in a partial state, you first have to understand the assumption that provisioning makes about itself and why that assumption cannot be fully honored. Provisioning is designed as if it were a transaction. The intent is clear, the whole thing succeeds or the whole thing fails cleanly. CloudFormation calls this atomic deployment. Terraform has a state file designed to track exactly what exists. Kubernetes uses rollouts with rollback capabilities. Every major infrastructure tool is built around the premise that you should never end up between states. But provisioning is a distributed operation. It touches dozens of independent systems: the Compute API, the IM service, the DNS service, the load balancer service, each of which is a separate system with its own state, its own failure modes, and its own consistency guarantees. None of these systems share a transaction boundary. There is no distributed transaction coordinator watching over all of them, ready to roll back every participating system in perfect synchrony if one of them fails. What exists instead is a best effort rollback, an orchestrator that, upon detecting a failure, attempts to undo what it did in reverse order. This works well when the failures are clean. A resource that was never created can simply be skipped in the rollback. The problem is that failures are frequently not clean. A resource that was created and then partially configured is not cleanly deletable. The partial configuration may be in an invalid state that the delete API rejects. A resource that was created and immediately claimed by another system. A load balancer that registered the new instances. A service mesh that added the new endpoints. A monitoring system that started scraping the new targets cannot be deleted without first detaching it from those dependents. And the orchestrator performing the rollback doesn't always know about those external dependencies because they were created by systems outside its scope. This is how you get rollback failed. Not because the rollback code is buggy, because the state of the world when the rollback runs is more complex than the rollback was designed to handle. Partial provisioning states are not all the same. They have distinct shapes, each with different implications for what's safe to do next. The first shape is orphaned resources. These are resources that were created successfully during the provisioning attempt and either survived the rollback or were never targeted by it. They exist, they may be running, they are consuming cost, they are not connected to anything that uses them productively, or worse, they are connected to things that are now relying on them incorrectly. An orphaned EC2 instance that's running but serving no traffic is a cost problem. An orphaned security group that was created with overly permissive rules and was never attached to anything productive is a security problem. An orphaned database snapshot that contains production data and has no retention policy is a compliance problem. Orphaned resources are invisible to your deployment tooling after a failed rollback. They exist outside the managed state, which means they won't appear in future plans, won't be cleaned up automatically, and won't be flagged unless you specifically go looking for them. The second shape is split configuration. This is the state where some components of your system have been updated and others haven't, and the two halves are now inconsistent with each other. A new version of a service is partially deployed. Some instances are running the new version, some are still on the old version, and the new version has a different API contract from the old one. Clients that land on new instances get different behavior from clients that land on old instances. Errors are intermittent, symptoms are confusing, and the root cause that the system is simultaneously two versions of itself is not obvious from any individual service's metrics. The third shape is stuck transitions. These are resources that are not in a stable state, neither the state they were in before the provisioning attempt, nor the state they were trying to reach. A database that's in the middle of a schema migration that was interrupted. A container that's in terminating state and cannot be deleted because a finalizer is running that requires a resource that no longer exists. An auto-scaling group that's in the process of replacing instances and has stopped halfway through. These resources are not failed, they're suspended mid-operation, and interacting with them incorrectly during this state can make the situation significantly worse. Each shape has different risks, different cleanup approaches, and different answers to the question of whether it's safe to retry the provisioning operation. The instinct when a deployment fails is to retry it, fix the error, run it again, let the tooling sort out the state. In most software contexts, this instinct is right. A failed function call can be retried. A failed network request can be retried. Retrying is safe when the operation is idempotent, when running it again produces the same result as running it once. Cloud provisioning operations are frequently not idempotent, and in a partial state, retrying without first understanding what already exists can make the situation significantly worse. Consider what happens when you rerun a CloudFormation stack that failed mid-deployment and left orphaned resources. CloudFormation doesn't know those orphaned resources exist. They're outside its managed state. When it tries to create the resources with the same names, it may fail immediately because the names are already taken. Or it may create duplicate resources with different names. Now you have two of everything, and the stack succeeds. Into a state where your infrastructure has both the orphaned originals and the new duplicates, pointing at different things, being used by different parts of your system. Consider what happens when you run Terraform apply on a workspace where a previous apply timed out. Terraform reads its state file, sees that some resources weren't recorded, and plans to create them. But some of those resources may already exist in the cloud, created during the timed-out apply, just not recorded in state. Terraform attempts to create them. The cloud returns an error saying they already exist, and the apply fails again, this time with a different error than the original, which makes it look like a new problem when it's actually the original problem wearing a different mask. Recovery from a partial provisioning state has a specific order that cannot be skipped. Inventory first. Before touching anything, establish what actually exists. In AWS, this means querying the actual state of every resource type that the failed operation touched, not reading the CloudFormation stack outputs or the Terraform state file, but querying the cloud APIs directly. Cross-reference what exists against what the tooling believes exists and against what the target state should have been. The gaps between these three views are the partial state. Classify before acting. For each resource in the partial state, determine which of the three shapes it is, orphaned, split, or stuck, and assess whether it's safe to remove, whether it has external dependence, and whether removing it will impact anything currently serving traffic. This classification cannot be automated in the general case because it requires understanding the semantics of your specific system, not just the resource types involved. Cleanup in dependency order. Resources have dependencies. A security group cannot be deleted while instances are using it. A subnet cannot be deleted while network interfaces exist in it. A VPC cannot be deleted while subnets exist in it. Attempting to delete in the wrong order will fail, and the failure may itself leave things in a worse partial state. Dependency order for deletion is the reverse of dependency order for creation, and it needs to be followed as carefully during cleanup as during the original provisioning. Verify before retrying. Once the partial state is resolved and the world is back in a known good baseline, the original provisioning operation can be safely retried, not before. The retry into a clean state will succeed or fail cleanly, and a clean failure is vastly easier to diagnose and recover from than a failure into a partial state that was already partially recovered. Rollback failed is not a disaster. It's a description. A description of a system that tried to clean up after itself and couldn't, because the state it created was more entangled than the cleanup process was designed to handle. The engineers who recover from this quickly aren't the ones who know the right incantation to force the stack into a good state. They're the ones who understand what a partial state actually is, which of the three shapes it takes, what it means for the components currently in it, and why the inventory step comes before any other action. Half-built is worse than not built. Not because half-built systems are noisier, they're usually quieter. Because half-built systems look like they might be okay. They exist in a way that feels recoverable without much effort. That feeling is the danger. The system that looks like it might be okay is the one that lets you skip the inventory, retry too soon, and find yourself in a partial state of a partial state, further from known good than you were when you started. Inventory first. Every time, no exceptions.